Probably the biggest puzzle in physics, wouldn't you say?
Oh, definitely. The massive elephant in the room.
Smooth curve in spacetime works beautifully.
Incredibly well.
And then quantum mechanics. Equally amazing, but it paints this picture of tiny, discrete packets of energy probabilities. It's just fundamentally weird, works perfectly for atoms and particles.
But they just don't mesh. Not at all. When you try to bring them together, especially down at the tiniest possible scales, the Planck scale.
Which is like 10 to the minus 35 meters. Unbelievably small.
Right. Down there, the theories just, well, they break down. They give nonsense answers. It's like this impassable chasm.
So what if the problem isn't just patching them together? What if space-time itself isn't the bottom layer?
Ah, now you're getting to it. Moving beyond maybe old ideas like that passive luminiferous ether everyone used to talk about.
Which was debunked, yeah.
Completely. But maybe towards something, well, more active, where space-time emerges from something else, almost like an ether that acts, you could say.
Okay, so that sets the stage. What's the specific angle for this deep dive then?
We're going deep into a model called the Quantum Vibrational Universe. The core idea, the mission really, is to see if we can understand how everything space-time, matter, gravity, the whole lot might emerge from just one underlying reality based on vibrations.
Vibrations.
Yeah, vibrations. The central idea is that the universe fundamentally isn't empty space. It's more like an elastic medium, but with a discrete structure, like a crystal, a world crystal.
A world crystal, okay.
And in this picture, space-time is just the geometry of this crystal. Matter turns out to be quantized sound waves, phonons moving through it, and gravity. Gravity is just the crystal sort of stretching and bending in response.
Wow, okay, that's a big picture. Let's break it down. Start with the crystal itself. This foundational idea that space-time isn't smooth.
Exactly. It's not continuous. It's a lattice, like a grid, but incredibly fine. The spacing is the Planck length, that 1.6 times 10^35 meters number.
So below that length, things just don't make sense in the usual way.
Right. You hit a fundamental limit, a minimal length. They call it a hodon. It's like the universe's pixel size. Below that, classical ideas of space and time just dissolve.
And you mentioned this isn't totally out of left field. Other theories hint at this.
Oh, yeah. Loop quantum gravity, for example, talks about space being made of discrete loops or nodes. And the whole idea of space-time foam suggests space is bubbly and chaotic at the Planck scale. So a granular structure isn't unprecedented.
Okay, so we have this crystal. How does its structure relate to, well, the shape of the universe, the geometry we actually observe?
This is where it gets really cool. A physicist named Hagen Kleinert made this connection. He showed that if you have a crystal, like a real physical crystal, and it has defects, imperfections in its structure.
Like cracks or something missing?
Exactly. Things like twists or places where the rows of atoms don't line up perfectly. He found a direct mathematical link between the geometry of a crystal with these defects and the geometry of spacetime that isn't just curved but can also be twisted. A Riemann-Cartan spacetime, technically.
So the crystal defects are the spacetime geometry?
In a sense, yes. Specific defects correspond to specific geometric features like disclinations. These are like rotational defects where the lattice is sort of twisted around a point. These become the source of what we call space-time curvature.
The very thing that causes gravity in GR.
Precisely. And then you have dislocations. These are more like translational defects where you have an extra half plane of atoms shoved in or one missing. These generate space-time torsions, a kind of twisting.
So matter making space-time curve. In this model, matter is just energy concentrating, right? And that concentration causes these defects.
That's the idea. Concentrations of vibrational energy, what we perceive as matter, induce these defects in the lattice. The Einstein tensor, DIN, which describes curvature in GR, essentially becomes a measure of how dense these disclination defects are.
Okay, but hang on. If the crystal has defects causing both curvature and this twisting torsion, why does GR work so well with just curvature? Where did the torsion go? We don't really see its effects on planets and stars.
Excellent question. That's addressed by the nematic world crystal idea. It proposes that very early in the universe, there was a kind of phase transition. Think of it like a liquid cooling and forming a liquid crystal.
Okay.
During this transition, the model suggests that dislocations, the torsion-causing defects, proliferated like crazy and then sort of condensed. This condensation effectively gave the torsion field a mass.
Gave it mass, like a particle.
Sort of. It means the force associated with torsion became very short range. It got screened out, kind of like how magnetic fields get expelled from a superconductor, the Meissner effect. So its influence basically vanishes over long distances.
Ah, I see. But the curvature defects, the disclinations.
They remain dilute, spread out, so their effects, the curvature, stayed long range. That's why GR, which describes curvature but not torsion, works so well for the large-scale universe. Torsion would only really matter at incredibly high energies, near the Planck scale.
Okay, that makes sense. So the universe is this crystal lattice. What's actually moving or vibrating in it? You mentioned phonons.
Right. Phonons are the fundamental excitations. They're the quantized collective wiggles of this world crystal lattice. Think of them as the basic sound waves, but quantized, that can travel through this crystal.
And they arise because the universe crystallized.
Yeah, they're seen as what physicists call Nambu-Goldstone bosons. They appear when a system spontaneously breaks a symmetry in this case, the smooth, continuous symmetry of whatever existed before the crystal formed. The crystallization itself creates these fundamental modes of vibration.
And you said there are different types.
Two main types, crucial for understanding particles. First, acoustic phonons. These are like long wavelength vibrations where nearby parts of the lattice move together in phase, like a standard sound wave.
Okay.
For small amounts of energy or momentum, they behave like massless particles moving at a constant speed, the speed of sound in this crystal medium.
And these are?
We identify these with massless force carriers, photons, definitely. Possibly gravitons, the hypothetical particles of gravity.
Okay, massless particles. What's the other type?
Optical phonons. These are often more complex vibrations, maybe different parts of the lattice unit moving against each other. The key thing here is they have a minimum energy, a non-zero frequency. Even if they're not really moving across the lattice, there's an energy gap.
An energy gap. And that's important because
this energy gap, this minimum vibrational energy, is proposed to be the origin of rest mass for elementary particles.
wow, okay. So mass isn't fundamental, it's just the minimum energy needed to get this particular type of vibration going.
Exactly. And one more quick point. The crystal structure itself imposes a natural limit on how short the wavelength of these phonons can be related to the lattice spacing. This limit, the first Brillouin zone, acts as a fundamental cap on momentum.
Which helps with those infinities in quantum field theory.
Precisely. It naturally tames the ultraviolet infinities without needing extra mathematical tricks.
Okay, let's unpack this. This feels like it changes some really fundamental things. What about the speed of light, c? We always think of that as the universal constant.
Right. It's usually postulate number 1 in relativity. But in this quantum vibrational universe model, c is no longer fundamental.
Not it.
Nope. It becomes an emergent property. It's simply the maximum speed at which these phonon excitations, these vibrations, can travel through the world crystal.
Like the speed of sound in air is the max speed for sound waves.
Exactly like that. The speed of light, c, becomes the maximum group velocity for any wave packet in this spacetime medium. It gets a physical explanation based on the crystal's stiffness and its discrete structure, rather than just being a given axiom.
That's a big shift in thinking. Now let's connect this to matter. Wave-particle duality is one of the cornerstones and weirdest parts of quantum mechanics. De Broglie's idea. Everything has a wavelength. Usually that's just stated as fact.
It's a foundational postulate, yeah. A brute fact, as you say. But this model offers a path to actually derive it. Wave-particle duality stops being this deep paradox and becomes almost, well, intuitive, if you accept the premise.
How so?
The core identification is this. An elementary particle, like an electron, isn't a tiny point that sometimes acts like a wave. It is a localized, stable-ish wave packet. It's a ripple, a superposition of these fundamental phonon modes of the world crystal.
So saying an electron is fundamentally a wave in this space-time crystal.
Exactly. It's a wave excitation, and when you measure it, you force it to deposit its energy in one place, making it look particle-like. But its nature is wave-like.
Okay, so particle properties translate directly.
Yes. The particle's momentum is just the total momentum carried by all the phonon waves making up the packet. Its de Broglie wavelength is related to the main wavelength in that packet. And its velocity is the group velocity, how fast the overall packet moves through the crystal.
Here's where it gets really interesting for me. How does this model explain something as fundamental as mass? You touched on it with the optical phonons.
Right. So the model can reproduce the standard relativistic wave equations, like the Klein-Gordon equation for simple particles. And the truly profound result is what we discussed. Mass isn't intrinsic. It's a measure of the minimum energy needed to excite that particular vibrational mode. Mass comes directly from that energy gap, cogap, of the optical phonon branch, MOS2.
So a particle with mass is an optical phonon excitation.
Or at least its mass originates from that optical branch's energy gap. Massless particles, like photons, they correspond to the acoustic phonons, where the energy gap is zero. No minimum energy needed to get them going.
Okay. What about particles like electrons, fermions with spin? That seems trickier than just a simple vibration.
It is more intricate, definitely. Getting the Dirac equation for spin-12 fermions likely involves more than just simple displacement. You might need to consider the polarization of the phonons, like, are they vibrating along the direction of travel or perpendicular to it? Or maybe it involves more complex topological features of the excitations in the lattice, like twists or braids in the vibrational patterns. That's an active area of research.
But the basic dictionary holds. Particle is a wave packet, mass is an energy gap, spin is some kind of complex vibration characteristic.
That's the mapping, yes.
Okay.
It provides an emergent analog for all these properties within the vibrational framework.
Okay, let's talk about deriving gravity itself. You mentioned analog gravity, this idea from condensed matter physics, where sound waves, say, in a fluid, can act like they're in curved spacetime. How does that help here?
Analog gravity is the conceptual key. It shows that even in mundane systems, the collective behavior of waves or disturbances can mimic gravity. The waves feel an effective metric determined by the properties of the medium they're traveling through, its density, its flow speed, etc.
So you apply that idea to the world crystal.
Exactly. We want to derive the Einstein field equations, EFE. Let's break it down. First, the source term, T, the stress energy tensor. What causes gravity?
In this model, it must be the vibrations themselves, right?
Precisely. There's only one fundamental field, the crystal's vibration or displacement field, U. So the source of gravity is the stress energy contained in the phonon field itself. A particle is just a localized lump of this vibrational energy and momentum.
Okay, source is the vibrations. What about the geometry side? Goon, the Einstein tensor.
That's the emergent part. The geometry isn't fundamental. The effective metric, Moon, that the phonons experience as they propagate depends on the bulk properties of this phonon fluid, its density, pressure, velocity. Once you have that effective metric, you can use the standard tools of differential geometry to calculate the curvature and thus the emergent Einstein tensor, Boon.
So you have the source, the vibrations, and the geometry, how vibrations experience the crystal. How do they connect to give the field equations?
That gives you the quantum vibrational field equations, or QVFE. Symbolically, it looks like yin, kitin. It's a statement of profound self-consistency. The way the vibrations are distributed locally, the source, titin, must be consistent with the effective geometry they collectively create for their own propagation.
A feedback loop.
Exactly. Gravity emerges as the phenomenon that enforces this self-consistency. The shape of the crystal dictates how vibrations move, and the vibrations, in turn, shape the crystal. It's dynamic.
So what does this all mean for fundamental constants like gravity's strength, G? Is that still fundamental?
Nope. Just like C, the gravitational constant G is no longer fundamental in this picture. It emerges. Its value is determined by the actual physical properties of the world crystal, its stiffness, its density, its lattice spacing.
So the strength of gravity depends on the material properties of spacetime.
In a very real sense, yes. It's not just some number plucked from thin air. It's tied directly to the underlying structure. And the cosmological constant, the thing driving cosmic acceleration, that also gets a natural explanation. As the residual ground state energy, or maybe an intrinsic tension, of the world crystal when it's in its empty vacuum state, it's the energy of the crystal just sitting there.
That's a radically different perspective on G and lambda. Okay, this is all very elegant theoretically, but let's get to the really exciting part. What are the big, maybe even testable implications?
This is where it gets really interesting, yeah. First, just reinforcing the core idea. Gravity isn't fundamental, it's emergent. Like elasticity. Think about it. You press on a solid, it develops internal stress and strain. Curvature is like the strain field in the space-time crystal caused by the stress of energy and momentum.
So a planet creates stress, strains the crystal, and things follow that strain.
That's the picture. Particles follow the lines of strain, which we see as gravity. Second big implication, Lorentz invariance.
The idea that physics looks the same regardless of your constant velocity.
Right, a cornerstone of relativity. Now, a discrete lattice, like our crystal, inherently breaks perfect Lorentz symmetry. There's a preferred frame, the frame of the lattice itself.
Uh-oh. Isn't that a problem? Experiments confirm Lorentz invariance incredibly well.
It seems like a problem, but the model predicts Lorentz invariance emerges as an extremely good approximation at low energies, the energies we usually deal with. Think of waves on water at long wavelengths. The water looks continuous, but zoom in and you see molecules.
Okay, so it's approximate. Does that mean it could be violated?
Yes. Crucially, the model predicts tiny violations of Lorentz invariance, LIV, that become more apparent as a particle's energy gets closer to the Planck scale. One effect would be an energy-dependent speed of light, or neutrinos. Very high-energy particles might travel slightly faster or slower than lower-energy ones.
And we can look for that.
We can, by observing high-energy photons or neutrinos from distant cosmic events like gamma-ray bursts or active galaxies. If particles starting at the same time but with different energies arrive here at slightly different times after traveling billions of light years, that could be evidence for LIV.
Has anyone seen anything?
The constraints are very tight, meaning Lorentz invariance holds extremely well. But there have been some tantalizing, though not conclusive, hints in some observations. It's an active area of research.
What else? You mentioned singularities earlier.
Right. The discrete nature of the lattice provides a natural cutoff. You can't squeeze things infinitely small because there's a minimum length, the lattice spacing. This potentially resolves the infinities predicted by GR at the center of black holes and at the Big Bang. The smooth, continuous description just breaks down there, preventing a true singularity.
It's huge. And the cosmological constant, lambda.
As I mentioned, it gets interpreted as the crystal's ground state energy or tension. This could potentially solve the fine-tuning problem, why lambda is so incredibly small compared to theoretical predictions. Maybe the crystal is just naturally very relaxed.
And dark matter and dark energy. Could this model explain those too?
It offers a potential unification. Dark energy could literally be this ground state tension of the crystal and dark matter. Instead of needing exotic new particles, perhaps it's an effect of the crystal's elastic response. Ordinary matter strains the crystal, and maybe this strain extends much farther than expected in standard GR, creating an effect that looks like extra gravity, like a dark matter halo, due to the crystal's large-scale elastic properties.
Wow. Okay, so dark matter and dark energy might just be properties of the space-time medium itself. That would be revolutionary. Are there other specific ways to test this, other experimental signatures?
A few others are predicted. One is vacuum birefringence. If the crystal isn't perfectly isotropic, if its elasticity is slightly different in different directions, it could cause the polarization of light to rotate as it travels vast cosmic distances.
Like light passing through some crystals we know.
Exactly. People are looking for this effect in light from distant quasars and in the cosmic microwave background. Again, there are some intriguing hints, like a potential signal in the Planck satellite data, but nothing definitive yet.
Interesting. Anything else?
Possibly MOND-like effects. MOND is an alternative theory to dark matter, suggesting gravity behaves differently at very low accelerations. In this crystal model, maybe the crystal's elastic response becomes nonlinear, different from standard GR in these low acceleration regimes, like the outskirts of galaxies. Precision galaxy rotation curve measurements could probe this.
Okay.
And one more. A high-frequency gravitational wave cutoff. Just like a real crystal can't vibrate faster than a certain frequency determined by its structure, this world crystal would impose a maximum frequency on gravitational waves. If we could measure the background hum of gravitational waves across all frequencies, finding a sharp cutoff at high frequencies would be incredibly strong evidence, maybe even a smoking gun for a discrete spacetime.
So, quite a few potential avenues for testing, even if they're incredibly challenging. Looking ahead then, what are the biggest hurdles, the next steps for developing this kind of theory?
There are definitely significant challenges. A big one is incorporating gauge forces. How do electromagnetism and the weak and strong nuclear forces arise? They aren't obviously just vibrations. Maybe they relate to extra properties at each lattice site, or perhaps more complex topological features like knots or braids in the defect patterns.
That sounds complicated.
It is. Then there's the fermion problem, really getting a solid derivation for particles like electrons with their spin-12 nature and the Pauli exclusion principle, which stops them from piling up in the same state. That's critical.
Right, explaining why matter takes up space.
Exactly. And on the large scale, cosmological evolution. We need to apply these QVFE equations to model the universe's history, perhaps starting from an initial crystallization phase transition instead of a Big Bang singularity, and see if it reproduces inflation, structure formation, all of it.
And bridging the gap between the quantum crystal and our smooth reality.
That's the quantum to classical transition. How does the definite, predictable spacetime we experience emerge from this underlying quantum lattice, which must be constantly fluctuating? That likely involves understanding decoherence in this context. Lots to figure out.
Absolutely. But despite the challenges, you have to admit, it's an incredibly compelling vision. A universe where all this mind-boggling complexity, particles, forces, space-time geometry, all bubbles up from the relatively simple physics of vibration. So think about that. The universe might not be this static void with bits of matter scattered in it. It might be this single, vast, vibrant, elastic crystal. And everything we see, everything we are, is just a part of its ongoing vibration.
It really makes you wonder, doesn't it? If reality truly is this grand symphony of vibrations, what does that mean for us, for our consciousness? And what other incredible notes, what other physics might still be waiting to be discovered in the universe's ultimate song? It suggests that the deepest truth might lie not in finding the ultimate particle, but in understanding the ultimate pattern of motion.